your substrate here to go that way. But what doesn't happen is the enzyme, when it bounds an inhibitor, goes to the product. Now, there are basically different flavors of this kind of inhibition depending upon whether the inhibitor binds to the free enzyme, the enzyme substrate complex, or both. And we're going to start by talking about the situation where, what if the inhibitor only binds to the enzyme substrate complex? Like the inhibitor won't bind unless you bind to the enzyme substrate complex. So that's what's known as uncompetitive inhibition. So again, the enzyme only binds at the active site. I mean, what did I say? Enzyme inhibitor only binds the ES complex. And so we can sort of simplify that by saying we have the enzyme plus substrate forms the enzyme substrate complex, and then we go enzyme plus product. But here we can bring in our inhibitor and have the enzyme inhibitor. Now what this makes this kind of funky is, so what this ends up doing is it basically lowers the Vmax by reducing our enzyme substrate complex. By sequestering it away, we're going to reduce our Vmax, okay? But the interesting thing is the effect on Km. Because basically what we have is now, by having the inhibitor, we have another pathway for what happens to ES. Okay, so what that means is by adding the inhibitor from Le Chatelier's principle, I have to remember that, sort of principle of mass action, you suck more of this away into the enzyme substrate, you suck this equilibrium to the right. Okay, so the ultimate outcome of that is that this actually lowers the apparent Km. It makes it appear as if the enzyme actually has a greater affinity for the substrate. And it also lowers Vmax. So if we look at our kinetic curve, and here's our uninhibited reaction. Here's our Vmax, so this is uninhibited. And then here is our Km uninhibited. So now when we add our inhibitor, we're going to lower Vmax. So I'm going to draw another line here. So this is the inhibited. And so this is Vmax inhibited. but our Km actually gets shifted to the left. Okay, so our Km, if this is our half Vmax of the inhibited one, our Km is going to end up being something like in here. And so this is going to kind of go up more steeply than the uninhibited reaction, but it's going to level out at a lower level. That's because sometimes it's kind of hard all to see. The easier way to see it is actually back to our double reciprocal plot. Here's our uninhibited line. And what happens here is our Vmax is lower, but our Km is actually lower as well, and so you end up getting a parallel line here. So here's our inhibited. So again, this is 1 over Vmax, and then uninhibited. This is 1 over Vmax inhibited. It's right here. This is minus 1 over Km uninhibited. This is minus 1 over Km inhibited. All right. One other thing I should point out of this is actually our ratio, our Km to Vmax ratio is the same in this scenario. And so this slope here is Km over Vmax. And you notice it's the same between both of them. All right. So that's the unique situation when an inhibitor only binds the enzyme substrate complex. Okay, now the reality is it usually binds both of those. Okay? And so that's what's known as mixed inhibition. Is the inhibitor binds either the free enzyme or the enzyme substrate complex. So it basically does sort of this. It'll do either one. Now in this case, the Vmax is lowered. The effect on Km will depend on how much whether it tends to bind the enzyme substrate complex better or the enzyme substrate or the free enzyme better. The more it binds if it prefers the enzyme substrate complex, it's going to tend to lower Km. If it prefers the enzyme, then it's going to tend to increase Km. So it's just going to depend upon the relative affinity. So effect on Km depends on relative affinity for ES, which lowers Km, or E, which raises Km. Now, there's a unique situation within mixed inhibition in which the inhibitor has exactly equal affinity for the enzyme and the enzyme substrate complex. If equal affinity, then there's a special term for it known as non-competitive inhibition. Now this seems like perfectly designed just to confuse students, right? We've got uncompetitive. What's the difference between uncompetitive inhibition and non-competitive inhibition? The difference is uncompetitive inhibition has an inhibitor binding exclusively the enzyme substrate complex. Uncompetitive, the inhibitor binds the enzyme substrate complex and the free enzyme with equal affinity.
Can you say that again?
Yeah.
Can you say that again? Can you say that again? The difference between...
Yeah, so uncompetitive inhibition, the inhibitor only binds the enzyme substrate complex. Non-competitive inhibition, it binds both the enzyme substrate complex and the free enzyme with equal affinity. Honestly, to find an enzyme that has true non-competitive inhibition is relatively rare. Most enzymes, you'll see kinetic treatment, they'll say it's mixed inhibition. It affects both Km and Vmax. Because in this situation where we have equal affinity, Km is unchanged, and Vmax is lowered. Now, one of the reasons I think that this whole non-competitive concept survives is just because it's graphically, it looks pretty cool. Basically, if we do our one, again, this is non-competitive inhibition. we have our uninhibited reaction. Again, remember this is -1 over Km here. So if we know Km has changed, this spot's not going to change, but our Vmax is lowered. So you get so this is uninhibited here, and then this is inhibited here. So I'm just going to do this because you'll see these problems over and over again. Get them in 162 if you haven't had them already. These are classic interpret the double reciprocal plot problems. We're going to kind of throw 3 different situations up here. All these are 1 over V0 versus 1 over S. 1 over V0 versus 1 over S. 1 over V0 versus 1 over S. We're all going to have our uninhibited reaction here. We've seen 3 different scenarios. One in which it looks like this. One in which it looks like this. And one which it looks like this. And the question usually is something, okay, what kind of inhibition do you see? All right, anyone remember what this one is?
Competitive.
No, this one, this is supposed to meet exactly right here. So this is 1 over Vmax. This is -1 over Km. So this is the one where Vmax is unchanged, but we actually raise our Km. It is a reversible, and this is, these are all reversible inhibitions actually, but this is competitive inhibition. Because what we've done is Vmax is same, thus our 1 over Vmax is the same, Km is higher. This is where you have to do a little mental gymnastics. If Km is higher, then -1 over Km actually shifts to the right. This one here, you know what this one is? This one's the uncompetitive. This one, Vmax is lower. And Km is higher. No, I mean Km is lower. Lower, and Km over Vmax is the same. And then this one here is the non-competitive. And this one, Vmax is lower. Km is unchanged. The other thing I just mentioned, because I've just been sort of saying, okay, with and without the inhibitor, it actually, the effect, the more inhibitor you add, the greater the inhibition. So you basically, if this is the uninhibited, the more inhibitor you get, the steeper and steeper it gets. You always, because Vmax is unchanged, you always rotate around that 1 over Vmax point. The steeper and steeper it gets. Similarly, this one, the more inhibitor you add, the further and further it goes up. And then this one, for the non-competitive, the more it would basically pivot that way as you add more and more. So sometimes you'll see these as a family of lines. It'll say increasing inhibitor, and you'll see a family of either parallel lines for uncompetitive inhibition, or a family of lines in which this point is the same, this is minus 1 over Km point is the same, or a family of lines in which it all pivots around the 1 over Vmax. Handy thing to remember is the inhibited line always is the one that is steeper and above the uninhibited line here. Steeper or above the uninhibited line. Anyway, so you'll see those in the problems. I believe I assigned some problems that relate to this. We'll see this stuff in 162. 162, we have you do an inhibitor, right? If I remember right, what kind of an inhibitor is it? Do you remember it? Have you figured it out yet? You're doing that too? Oh, good, this is like perfect timing. Like once in the semester, we have perfect timing. All right. All right, so that's good. That's enzyme inhibition. And so, again, where this applies, practically is, if you're doing drug development work, you're trying to develop an inhibitor, you synthesize a molecule, and now you're trying to act and see if it actually inhibits a particular enzyme. One of the first things you're going to ask is, like, if you designed it to be a transition state to show it to be a competitive inhibitor, well, does it really act as a competitive inhibitor, or does it act in some other way as an uncompetitive? And usually, typically, most inhibitors end up being mixed inhibitors. I should say most inhibitors that bind away from the active site end up being mixed inhibitors. All right. Now we're going to move on and talk a little bit more about in vivo regulation of enzymes. A lot of this is placed sort of in the context of sort of designing inhibitors from a technological standpoint for applications in as drug targets or these sorts of things, or as drugs or these sorts of things. But now what I want to sort of talk about is in vivo regulation of enzyme activity. And this leads us to talk about allosteric regulation. And I think I'm going to start another little outline here. So this is in vivo So, we have a bunch of metabolic processes going on. You'll be talking about this a bunch in the second semester. They're constantly being turned on and turned off. It's basically when you eat a meal and your liver is starting to store away sugars in the form of glycogen, so glycogen synthesis gets turned on. A few hours later, it's been a while since you've eaten, now you're breaking down that glycogen and you integrate the sugars, and then you're then you're metabolizing those. So you're turning a pathway on, turning a pathway off. That's over an hour standpoint. But even, I think I've given this example before. If you're walking up that flight of stairs and you start huffing and puffing, you've turned on a bunch of metabolic pathways to do that. And then when you get on top of the stairs, you recover a little bit. You're turning those pathways off. So the metabolic pathways are constantly being turned on and turned off. So we say, well, how does that actually happen? First of all, so we're given an overview of the whole processes. So we're thinking of, a pathway like A goes to B, goes to C, goes to D. Maybe this is, glucose going down to pyruvate and glycolysis, or maybe it's phosphoenolpyruvate and glyceraldehyde 3-phosphate going to cholesterol, something like that. You have a variety of different pathways. But so one of the ways you can do it is just by regulating. So if we were going to ask, what controls the speed of this reaction? Each one of these steps is catalyzed by an enzyme, right? We'll call it, enzyme 1, enzyme 2, enzyme 3. Each one of these reactions is catalyzed by an enzyme. What controls the rate of that conversion of A to B? Well, one is just the availability of A. So it's just the regulation by controlling substrate availability. Now what controls the speed of that reaction is just how much A you make. And then that's going to depend upon all the sort of upstream reactions that actually are there to generate A. Okay, so that in some ways this kind of begs the question a little bit. It's true that some reactions might be substrate limited, but most of them are actually regulated by the actual activity of the enzyme. Again, remember that these reactions, in almost all biological reactions, these reactions occur at a negligible rate in the absence of the catalyst. Okay, so sort of the more meaningful question is this regulation by altering our total enzyme. So if we remember our Michaelis-Menten equation for the velocity of an enzyme-catalyzed reaction, the velocity is K2 times the total enzyme times S over Km plus S. So we talked about, in this first point, well, you can control this velocity by how much S you have in there, but you can also control it by the amount of enzyme that's actually there, the total enzyme. Okay, so what are some different ways of controlling the total amount of enzyme? One is transcriptional regulation. The enzymes of the Calvin cycle. This is the metabolic pathway that fixes carbon dioxide during photosynthesis. When the light comes on in the morning in a plant leaf, one of the first things that happens is all those enzymes are transcriptionally activated. That the genes encoding those enzymes are transcribed and the enzyme is made. And then we'll talk about later, at the end of the day, those things are broken down. So you're controlling regulation by the pathway just by controlling the amount of synthesis of that enzyme. So this is what transcriptional regulation. This is increasing transcription of the gene to generate more RNA that messenger RNA that encodes the enzyme. Now, just because you transcribe the gene doesn't necessarily mean the transcription is the making of the mRNA. the mRNA still has to be translated into the protein itself. So you can also have another level of regulation, which is translational regulation. And that's controlling the amount of the conversion of mRNA, the translation of the mRNA to the actual protein. So increasing enzyme synthesis from mRNA. Then finally, you can alter the total amount of enzyme there either by making more enzyme or controlling how fast it's broken down. So the third thing basically here is changing the rate of enzyme degradation. Basically, if you turn on the enzyme degradation pathway, you're going to lower the amount of enzyme. That's going to reduce the activity of the metabolic pathway. All right. So we can regulate by altering the total amount of enzyme, but we can also regulate by altering the catalytic power of the enzyme, by basically making it a better or worse catalyst. Or essentially another way of saying that is by altering K2, by having some sort of change in K2. And this is, well, either K2 or Km, really. Now, one way you can do that is to through covalent modification. And a good example of that is phosphorylation. A common way of doing that is phosphorylation. By phosphorylating a molecule, usually a serine or threonine residue, taking those alcohols and putting a phosphate on there, you change the shape of the enzyme to either make it more active or less active. This isn't the only covalent modification. Actually, your text gives an example of a protease that is activated by actually cleaving the peptide backbone in there, and it ends up altering its shape into a more active form. there are other examples, but a real common one is phosphorylation. Okay, the next way, again, we're altering the catalytic power of an enzyme, is for the enzyme to actually reversibly bind this reversible binding of small molecules that activate or inhibit the enzyme. This is known as allosteric regulation. And next Monday we'll come back and we'll finish that up. I'm not going to start that right here, but so what we're basically doing is by binding small molecules, we're altering the shape of the enzyme to make them either less good or more or better, not more good, better catalysts.